then with the lecture of Professor Dr. Hans-Peter Nachtnebel with the paper entitled Human Influences on Hydrological Cycle. Please, Professor, you can start your presentation.
Okay, thank you very much. You can see my presentation.
Not now.
But it's uploaded. What else do I need to do?
On the
screen?
Yes, and you click on your presentation.
Yeah.
It's okay. Start screen sharing.
Yes, yes.
It's okay.
Okay, now you can see. Thank you. So I'm pleased to contribute to this session, and I would like to speak about impacts on the mountain environment, especially on the hydrological cycle. And as usual, structure of my presentation is that I would like to put the emphasis on a methodology for assessing the human impacts and then assessing the impacts of climate change. And then I will provide some data from a case study. As you can see, my PowerPoint presentation includes a lot of transparencies, so I will skip several of them, but I have included them that those who are interested in can see in more detail how we model interventions by hydrological tools. So the objective is analysis of changes in the hydrological cycle and identification of impacts. Here I have a general graph how and where humans intervene into the hydrological cycle. So we start at the upmost level with respect to climate. So we intervene here at the global scale, and this has impacts on precipitation, and this has impacts on all the water flows, which are described here in a very general way. So downwards and upwards water flows. And then due to land cover, we have changed also these cycles. And due to technical engineering, we built reservoirs in the mountain. We have modified seasonality in runoff, etc. And then again, the land use having direct impacts on the soil layer. This has consequences for soil water storage. And finally, groundwater recharge, whatever we have in mind, and water abstraction from groundwater also modifies the cycle. So it's on one side climate, and on the other side, human interventions. We have impacts with respect to the water balance. We have impacts and changes in the seasonal pattern, in the frequency of extremes, and then also impacts on the soil due to erosion and sediment transport. This is not an exhaustive list, it's a general description. There are far more impacts on the water systems. Typical examples from my home country, we built a lot of reservoirs high up in the mountains with the main goal to store water during the melting period and to be able to utilize it throughout the year. Here you have a map of hydropower schemes distributed within Austria. Although it's a small country, we have, nobody knows precisely, but something like, including small hydropower, about 4,000, 4,500 schemes. The large dots here refer to the reservoirs in the mountain areas. The red dots refer rather to lowland schemes. We have also a lot of infrastructural development in the mountain areas with respect to roads, bridges, cable cars, tourism. They need water for artificial snowing. Water is needed to supply this resource. So all of these measures have impact on the maintainer's hydropower cycle. We build roads to support harvesting in the forest sector. We build roads for regional development, and you see very often the consequences. Erosion starts at this point and creates a lot of sub-problems. We harvest our forests, so we clear cut large areas, and this also has impacts on runoff pattern, etc. What kind of methodology do we have for assessing human interventions? One way is to do time series analysis. You see one example here. Another approach is that we do experiments. There are famous experiments with respect to clear cutting, gall-nut experience is documented quite well. So we study what happens if we make real experiments. We make comparative studies. This means we look for similar hydrological catchments, under similar hydrometeorological conditions, but different land uses. And then we try to compare. Or we apply detailed, physically based hydrological models, as you can see here. So we need different informations covering the whole area, soil type, land cover, elevation zones, subcatchments. Based on this information, we subdivide the catchments into elements, whatever it is, and for each element, we apply, for instance, a model like this one. They are, in principle, similar to each other, but numerous models are available, okay? What kind of tools, assessment tools we have with respect to climate change? Time series analysis, as an example you see here, changes in glacier areas taken from photos where we can delineate the extent of the glacier areas. Or we make time series analysis, we compare, for instance, on the basis of ground-based observations, how was the precipitation in 1950 and how is it in 2010 and how it will be in about 50 years. Data are obtained from climate simulation models. We can also study some elasticity measures to learn about the sensitivity. What happens if temperature goes up by 5%, precipitation goes down by 5%, what is supposed to happen? Or we make comparative studies, trading space for time. So we look for similar catchments, which are, with respect to the physical settings, altitudes, land use similar, but they are exposed to different climates. Or we use simulation data, but very often the scale is not really appropriate. So you need to downscale, and downscaling is very, well, demanding sometimes. I will not go into detail. Finally, you may find data covering with a high resolution your area. And then sometimes we use this sensitivity analysis. For instance, here you see an example where we have the response with respect to flood risk in a certain area. So we have left everything the same. We only changed the magnitude of the floods, and we could learn where additional damages might occur. So we could conclude from this map the sense, or to identify the sensitive areas in a certain region. We don't say this will happen, but we say if it would happen, this would be the consequences. And here I would like to present very briefly an example from a case study. It's a catchment of about 700 square kilometers in the altitudinal range from 200 to 1800 meters. And I will assess here the human impacts on the hydrological regime. What has happened in that area? Well, we had some implementation of engineering works, mostly flood levees in the downstream part. We had changes in land cover. So forested area has been substantially increased from about 25% to about more than 70% today. Increase in residential area has been also investigated, but this is rather of minor importance in that catchment. And then, due to the growth of forests, a lot of forest roads, as you have seen previously, had been developed. We have a high density network now in the forested area, and this is also some impacts on the collection of surface runoff. So these are the human interventions and what are the conifers, what are the consequences. And you can see here the changes in land cover between 1880 and 2010. In 1880, forested area was about 25, now it's 77%. There was also a change in the composition of forest trees, but that's another story. You see, at the same time, we had a substantial decrease in agricultural land and grazing areas from about 75 to 21. Increase in residential areas is not that big. We used here the COSERO model, which we had developed some, 15 years ago. It's a partly physically based model, but I don't want to sell something. So here you have a long list of different models which are widely applied, and more or less they perform in a similar way. How do we model something? Well, first, we define a spatial topology covering the whole basin. Could be a grid-based system, could be a hydrological response units-based system. We connect the units to subbasins. We assign parameters to each unit. And then we try to improve the parameters by calibration and validation. We check the efficiency by simulating the past. So we make an assessment of our model performance, and then we can do different simulations based on our assumptions. So how it would look like in the future, how runoff would be in the future by having a different input. So this is the general strategy. What kind of data are needed? Well, soil type, land cover, elevation zone, subcatchments. And when you intersect all of them, as you can see here, you get subunits, so-called homogeneous hydrological units. And each unit is in the same altitudinal range, has the same land cover, has the same same or similar soil type, and is in a certain subcatchment. Or you apply the grid-based approach, so it's more or less a similar approach, only the geometry is different. And then you know which element drains to which other element, and based on that you can finally calculate the runoff at any location in the catchment area. How to parameterize, for instance, now different vegetation. Well, what changes when we have a different vegetation? Well, the interception rate might change due to certain amount of snow or water which is stored by the vegetation layer. This has some impacts on the soil water balance, because it might change the penetration of water into the soil. The uptake of water from the soil is different if you have a forest stand, or let's say a bare rock stand, etc., etc. And this can be modeled, and as I said, I skipped. So we only need to know which parameters or which element in our model has to reflect this vegetation cover. And finally, we put all these things together, and in the upper elements, there might be storage of snow. In the lower elements, there might be at the same time rainfall. You see different land use patterns, and all together, the contribution from each element finally results in an output observed here, surface runoff, and this is what we really can observe. Then we calibrate. What does it mean? We modify slightly the parameters within a certain range to improve simulation observations for the past. We have a certain calibration period, and then we have a validation period. So we use unused data sets with the calibrated parameters and check if it's also working in with unused data. We need a fitting criterion. You should know about that. And for instance, here, this is from our catchment. The blue line is the largest flood observed, and we simulated it, and we can discuss now, is it useful or not? But I think the time is well represented, and the peak is more or less well presented. So we could conclude, we did that for our floods, we could conclude, well, the model seems to work reasonably. Okay, you compare peaks, etc., and you can compare now different situations. So here we have observed, and here we have simulated, and you can do that also, for instance, for the land cover from 1880 with only 25% of forest land. We have also small-scale hydropower utilization, but these are small schemes of a few hundred kilowatt hours, so they don't have that severe impacts. But let's analyze river training works. And you see the red lines indicate the development from 1910 onwards, and we come more and more to our recent conditions. And you see we have a lot of engineering works which have modified our major tributaries in the basin. What are the consequences? Here on the upper right photo, you see the levee, and this here on the right side is the river, and this was former floodplain. Due to the levee, we have cut off the floodplain from the river. Only in very extreme cases, this area will be flooded by overtopping of the levee. How to model that? Well, you need a hydraulic model, here without any levee and here with levee, and then you can see, due to losses in the retention capacity, some increase in the flood peak downstream is to be expected. And now, what are the consequences of these levee structures? And these levees have been developed in the range between a 10 years and a 30 years flood. These are old levees, mainly to protect, as you could have seen on the previous photo, to protect arable land. And here we have the changes on the horizontal axis, the changes in the flood peak. And here we have the peak flow. And what are the consequences due to the implementation of the levees? You see, up to about a 30 years flood, these levees have contributed to an increase in the peak flow downstream. but up to about the design level, about to a 30 years flood. And the higher the flood, the lower is the impact of the levees in this specific case. So based on our simulations, we could estimate what would be the impact of flood levees which have cut off a lot of inundation areas for the downstream part. And this is a quantification of that. Land use changes, well, development of residential areas and changes in forested areas. And here you see the flood peak, and here you see the changes in the flood peak. So what does it mean? If we, due to an increase in forested areas, we could reduce, not we, but the flood peaks were reduced by about 50 to 60% for the smaller floods. And the higher the flood peak is getting, the lower is the impact of the increased forested areas. So when you consider, for instance, 100 years flood, then the impact on the decrease of the flood would be around 15% only. How could that be explained? Well, the larger the flood event, the lower is the benefit of the forested areas, but for frequent to medium floods, you could benefit a lot from the forested area. But when you have real and extreme events needs a lot of rainfall. So independently, if there are forests or grazing land, everything is saturated with water. All the small natural depressions which store water are already filled up by a large flood, so the impact is getting smaller. What would have happened if the previous simulated flood from 1997, the largest we had observed in our data, would have happened under historic conditions? Then you see the increase would be about, and that's something, from 700 to 800 cubic meters due to the losses in forested areas. Not really big, but 100 cubic meters in flood peak is already something. Increase in residential area, the benefits, the deficits with respect to the flood peaks would it be about 0.5 to 1%, not more, because it's only local developed area. Very important is the road network. Roads of first and second order cover about 200 kilometers, but the forest access roads and agricultural roads, they are in total length of about 4,000 kilometers. And this means they need an area of about more than 30 kilometers. And considering the whole catchment is 700 square kilometers, that's already something. What are the consequences for that? As you can see here, this is typical for the region. First, you generate erosion. And secondly, you cut here the slopes, you drain the slopes, and on the side of this access road, you have a water collector and which collects all the water and releases it somewhere. This is here how it is reflected in the model. And conclusion is, well, in general, it increases the flood peak by about 1%. In small subcatchments, it could be much larger. Erosive processes have not been explicitly considered here. When we think about climate change, these are observations of runoff. So it rather looks like that due to increased temperature, mean annual discharge is decreasing. precipitation is so far more or less stable. When you think about maxima and maxima in discharge, well, no clear trend could be derived from our set of observations. Possible impacts, we run the hydrological model with 1 times CO2 and 2 times CO2 concentrations, and we concluded here what would be the impacts on runoff. It's a difficult graph, but the first column in black refers to observed. The red one refers to 1 times CO2, and the light blue one refers to, sorry, the red refers to 2 times CO2, and the light blue one. Yes?
Excuse me, 3 minutes.
Yes, good.
Until
Good. Thank you. So in general, we could say, well, it has some impacts on the runoff. There will be, in the next decades, a decrease in the mean annual runoff. There will be an increase in evaporation rates. No major changes in precipitation can be expected. When we summarize, so I would say, we have all the tools ready to describe and to assess the human impacts in the alpine environment. We can quantify that. Most of them can be quite nicely quantified. There are different tools available. So here I emphasized a hydrologic modeling approach for quantitative assessment of the impacts. I briefly described the various steps. In many of our catchments, alpine catchments, which we analyzed, we found that so far the direct human interventions are comparable to climate change impacts. This should not mean that we should forget about climate impacts. They are quite severe in some areas, but also direct human impacts are severe, and they overlap. So we should consider the sum of both. And this means that human interventions should be carefully considered in any planning and intervention in a mountainous environment. Thank you very much.
Thank you.